Earth once belonged to creatures unlike anything alive today, enormous and small, slow-moving and fast, peaceful and dangerous, all sharing a world ruled by dinosaurs. Over millions of years, these animals expanded into every corner of the planet, adapting to forests, deserts, rivers and skies with remarkable variety. Some grew to enormous sizes that reshaped the land beneath them, while others remained small and agile, surviving through speed and cleverness. Their world was constantly changing, driven by shifting climates, volcanic activity, and evolving ecosystems that pushed life in new directions. Through it all, dinosaurs remained the dominant force, shaping the balance of nature in ways that lasted for an immense stretch of time. Yet this long era eventually reached a turning point that ended their dominance and opened a new chapter in Earth's history. More than 4,500,000,000 years ago, Earth existed as a very different world. From the planet known today, there were no forests, no oceans filled with fish, no birds in the sky, and no animals walking across the land. The conditions that would eventually allow dinosaurs to appear were still unimaginably far in the future. Earth was a young planet undergoing constant change, shaped by powerful geological forces, intense heat, violent impacts, and chemical processes that would gradually transform its surface over immense spans of time. The formation of Earth began during the earliest stages of the solar system. Around a newly formed sun, enormous amounts of dust, rock fragments and gas moved through space. Tiny particles frequently collided with one another. Some collisions caused the particles to stick together, forming larger objects. As these objects grew, their gravitational pull became stronger, attracting more material from the surrounding region. Through countless collisions and mergers, larger bodies formed, eventually becoming the planets. The growing Earth experienced a period of constant bombardment. Large and small objects struck the young planet repeatedly. Every impact released tremendous amounts of energy in the form of heat. At the same time, radioactive elements inside Earth generated additional heat as they decayed. The combination of impacts, radioactive heating, and pressure from the planet's increasing mass caused much of the early Earth to become molten. Instead of solid continents and deep oceans, vast regions of the young planet were covered by molten rock. Temperatures were extremely high. The surface changed continuously as material melted, flowed, and cooled. Conditions were hostile to any form of life that exists today. As Earth remained molten, materials inside the planet began separating according to their density. Heavy elements such as iron and nickel gradually moved downward toward the center. Lighter materials remained closer to the surface. This process, known as planetary differentiation, produced Earth's internal structure. A dense metallic core formed at the center, surrounded by layers of rock that would eventually become the mantle and crust. The formation of the core had important consequences for the future planet. Movements within the metallic interior eventually generated Earth's magnetic field. Although the magnetic field would continue evolving over time, it became an important protective feature. It helped shield the planet from some of the charged particles constantly streaming outward from the sun. During the earliest stages of Earth's existence, the atmosphere was completely different from the one present today. There was no breathable oxygen. Instead, gases released from volcanic activity dominated the atmosphere. Volcanoes were widespread across the young planet. Molten material rose from the interior and erupted onto the surface. These eruptions released large quantities of water vapor, carbon dioxide, nitrogen, sulfur compounds, and other gases. Volcanic activity played a major role in shaping the planet's environment. The gases released from Earth's interior gradually accumulated above the surface, creating an atmosphere. This early atmosphere was thick and unstable. Temperatures remained extremely high, preventing liquid water from existing for long periods on the surface. As millions of years passed, Earth slowly cooled. Cooling did not happen quickly. The planet retained enormous amounts of heat from its formation. Nevertheless, temperatures gradually declined. The outer layers of molten rock began solidifying, producing the first crust. This early crust was very different from modern continents. It was thinner, less stable, and frequently destroyed by geological activity. New crust formed while older crust melted or sank back into the planet's interior. Earth's surface was constantly changing. As cooling continued, water vapor in the atmosphere began condensing into liquid water. Clouds formed in the sky. Rain fell across the planet. This rainfall continued over vast periods of time. Water collected in low areas, eventually creating the first oceans. The appearance of liquid water marked a major step in Earth's development. Water influenced nearly every process occurring on the planet. It helped cool the surface, transported dissolved chemicals, shaped rocks through erosion, and provided environments where important chemical reactions could occur. The earliest oceans were not identical to modern oceans. Their chemical composition differed significantly. Minerals dissolved from rocks entered the water. Volcanic activity added additional substances. The interaction between water, rocks, and atmospheric gases created complex chemical environments across the planet. Even after oceans formed, Earth remained geologically active. Volcanoes continued erupting. Large impacts still occurred. Earthquakes were common. Molten material moved beneath the crust. The planet was far from stable. One of the most important events in Earth's early history involved the formation of the Moon. Scientific evidence suggests that a large object approximately the size of Mars collided with the young Earth. The impact released enormous amounts of energy. Vast quantities of material were ejected into space. Some of this material eventually gathered together through gravity and formed the Moon. The collision dramatically altered Earth's development. It affected the planet's rotation, tilted its axis, and influenced future tides. The Moon would become an important factor in Earth's long-term environmental stability. After the Moon formed, Earth continued cooling and evolving. The crust became more extensive. Oceans covered large portions of the planet. Chemical interactions between water, rocks, and atmospheric gases continued reshaping the environment. At some point during these early stages, life emerged. Scientists continue investigating exactly how this occurred. The earliest living organisms were extremely simple. They were microscopic and lacked the complex structures found in modern plants and animals. The first life forms probably depended upon chemical reactions for energy. They lived in environments that would seem extreme by modern standards. Some may have existed near hydrothermal vents on the ocean floor, where heated water rich in minerals emerged from Earth's interior. Others may have lived in shallow waters exposed to sunlight. These early organisms were simple, but their appearance represented a profound change in Earth's history. For the first time, living systems were present on the planet. Over immense periods of time, these organisms reproduced, evolved, and diversified. The atmosphere at this stage still contained very little oxygen. Most early organisms did not require oxygen to survive. In fact, oxygen could have been harmful to many of them. A major transformation occurred when certain microorganisms evolved the ability to perform photosynthesis. Using sunlight as an energy source, these organisms produced oxygen as a byproduct. Over long periods, oxygen slowly accumulated in the oceans and atmosphere. This change happened gradually over hundreds of millions of years. At first, oxygen reacted with dissolved iron and other substances. Large deposits of iron-rich rocks formed as oxygen combined with minerals in seawater. Eventually, these chemical sinks became saturated. Oxygen began accumulating in the atmosphere itself. This event fundamentally altered Earth's environment. Rising oxygen levels created opportunities for new forms of life while causing difficulties for organisms adapted to oxygen-free conditions. Over time, more complex cells evolved. These cells contained specialized internal structures that improved their efficiency. The appearance of complex cells opened new possibilities for biological evolution. Organisms became increasingly diverse. Different groups adapted to different environments. New ecological relationships developed. For much of Earth's history, life remained confined to the oceans. Conditions on land were harsh. There was no protective layer of vegetation. Intense ultraviolet radiation reached the surface. Water was limited outside aquatic environments. Gradually, conditions became more favorable. Oxygen accumulating in the atmosphere contributed to the formation of ozone high above the planet. The ozone layer absorbed much of the harmful ultraviolet radiation arriving from space. This protection made life on land more possible. However, the transition from water to land took an enormous amount of time. Organisms first had to develop structures capable of preventing dehydration, supporting their bodies, and reproducing outside aquatic environments. While life continued evolving, Earth's geology remained highly dynamic. The crust was divided into moving plates. These plates shifted slowly across the planet's surface. Their movements created mountains, ocean basins, volcanic regions, and earthquakes. Continents formed, broke apart, collided, and reassembled. The arrangement of land and sea changed repeatedly. Climate patterns changed as continents moved into different positions. Long before dinosaurs existed, Earth experienced several episodes during which large portions of the planet were covered by ice. Massive glaciers expanded across continents. Global temperatures fell dramatically. These cold intervals lasted for millions of years. Between these cold periods, warmer climates often returned. Oceans expanded and contracted. Sea levels rose and fell. Life adapted to changing environmental conditions. As evolution continued, multicellular organisms appeared. Unlike single-celled organisms, these life forms consisted of many cells working together. Over time, multicellular life became increasingly complex. The oceans eventually contained a wide variety of organisms. Some filtered nutrients from the water, others moved across the seafloor. Predators evolved and hunted other organisms. Food webs became increasingly sophisticated. A major evolutionary expansion occurred hundreds of millions of years before dinosaurs appeared. During this interval, many major groups of animals emerged. Organisms developed hard shells, protective coverings, specialized limbs, and more advanced sensory structures. Marine ecosystems became increasingly diverse. Different species occupied numerous ecological roles. Competition, adaptation, and environmental change drove further evolution. Eventually, some plants began colonizing land. Early land plants were small and simple. They lacked many features seen in modern vegetation. Nevertheless, their presence altered the environment. Plants helped stabilize soil, influenced atmospheric chemistry, and created habitats for other organisms. As plants diversified, larger and more complex forms evolved. Animals eventually followed plants onto land. Early terrestrial animals faced significant challenges. They needed methods for obtaining water, breathing air, moving across solid surfaces, and reproducing successfully. Over time, these challenges were overcome through evolution. Diverse groups of land-dwelling organisms emerged. Arthropods became widespread. Over time, these challenges were overcome through evolution. Diverse groups of land-dwelling organisms emerged. Arthropods became widespread. Later, vertebrates expanded into terrestrial environments. The development of forests transformed Earth's landscapes. Large plants spread across extensive regions. Their roots altered soils. Their remains accumulated after death, contributing organic material to ecosystems. Atmospheric conditions continued changing. Oxygen levels rose and fell over geological time. Carbon dioxide concentrations fluctuated. Climate responded to these changes. Amphibians became important inhabitants of many environments. These animals retained strong connections to water, but spent increasing amounts of time on land. Their descendants continued evolving. One evolutionary innovation proved especially significant: the amniotic egg. This adaptation allowed reproduction away from water. Embryos developed within protective membranes that reduced dependence on aquatic environments. The emergence of amniotes marked a major turning point. These animals eventually gave rise to multiple lineages, including those that would later produce reptiles, mammals, and dinosaurs. Across the vast landscapes of the Triassic period, life was rebuilding itself after a time of enormous loss. Forests were gradually returning to regions that had once been devastated. Rivers flowed through broad plains, and new ecosystems were beginning to take shape. Many of the dominant creatures that had existed before were gone, leaving behind a world filled with opportunities for surviving species and newly evolving groups of animals. It was within this changing environment that the first dinosaurs emerged, beginning a story that would eventually influence life on Earth for more than 160 million years. The appearance of the first dinosaurs during the Triassic period was not a sudden event. Their origins can be traced through a long history of evolution that stretched back millions of years before the first true dinosaurs walked across the land. The animals that eventually gave rise to dinosaurs belong to a larger group of reptiles known as archosaurs. This group also included the ancestors of crocodiles, flying reptiles known as pterosaurs, and several other lineages that thrived during the Triassic. Archosaurs became increasingly important as ecosystems recovered from the devastating mass extinction that marked the end of the Permian period. The Triassic period began approximately 252 million years ago. Earth at that time was very different from the modern world. Nearly all major landmasses were connected into a single enormous supercontinent known as Pangaea. This immense landmass stretched across much of the planet and was surrounded by a vast global ocean. Because of its enormous size, many regions within Pangaea were located far from the moderating effects of the sea. Large areas experienced dry conditions, long periods without significant rainfall, and strong seasonal variations in temperature. The end Permian extinction had removed a tremendous number of species from both marine and terrestrial environments. Entire ecosystems collapsed, and many ecological roles became vacant. Recovery was slow and uneven. Some areas remained biologically impoverished for millions of years, while others began to support growing communities of plants and animals. The Triassic world was therefore a place of experimentation and change, where evolution had opportunities to explore new paths. The landscapes of the Triassic included deserts, floodplains, river valleys, coastal regions, forests, and open woodlands. Vegetation consisted mainly of seed ferns, conifers, cycads, ginkgos, and other ancient plant groups. Flowering plants had not yet evolved. Forests looked very different from those of the present day, and the plant communities that covered the land reflected environmental conditions that were often warmer and drier than those experienced in many regions today. As ecosystems recovered, a wide variety of reptiles began to diversify. Reptiles were particularly successful during the Triassic because many possessed features that allowed them to survive in challenging environments. Their eggs could be laid on land, reducing dependence on water for reproduction. Their skin helped reduce water loss, and many were capable of moving efficiently across large distances in search of food, mates, and suitable habitats. Among these reptiles, archosaurs emerged as one of the most important groups. Archosaurs possessed several anatomical features that distinguished them from other reptiles. Their skull structure, limb arrangement, and overall body design provided advantages that it would contribute to their future success. Over time, archosaurs diversified into numerous forms, occupying many ecological roles throughout the Triassic world. Some archosaurs became powerful predators. Others developed herbivorous lifestyles. Certain groups remained relatively small while others evolved larger bodies. This diversification created a dynamic environment in which many different lineages competed for resources and territory. The ancestors of dinosaurs evolved within this broader archosaur radiation. One of the defining characteristics that eventually distinguished dinosaurs from many earlier reptiles involved the position of their limbs. In numerous older reptile groups, the limbs extended outward from the sides of the body. In dinosaurs and their closest relatives, the limbs were positioned more directly beneath the body. This arrangement supported more efficient movement and allowed for greater endurance while walking or running. Although the earliest dinosaurs were not necessarily the largest animals of their time, their body structure provided important advantages that would later contribute to their success. The evolutionary path leading to dinosaurs involved several intermediate forms. Fossil discoveries from South America, Africa, and other regions have revealed animals that possessed a mixture of characteristics seen in both earlier archosaurs and later dinosaurs. These transitional species help scientists understand how dinosaur features gradually evolved over time rather than appearing suddenly. One of the most significant animals associated with dinosaur origins is the archosauriform known as. This small creature lived during the Middle Triassic and exhibited characteristics that suggest a close relationship with the lineage that eventually produced dinosaurs. Although not a true dinosaur, it provides valuable insight into the anatomical changes occurring among dinosaur ancestors. Another important form is which lived during the Middle Triassic. This animal possessed long hind limbs and a lightweight body. Its skeletal structure demonstrates features that were becoming increasingly dinosaur-like. Such creatures illustrate the gradual transition from earlier archosaurs to the first true dinosaurs. By approximately 230 million years ago, the earliest dinosaurs had begun to appear. These first dinosaurs were generally small to medium-sized animals. They did not immediately dominate terrestrial ecosystems. Instead, they existed alongside numerous other reptile groups that were often more abundant and sometimes larger. The early history of dinosaurs was therefore marked by coexistence rather than immediate dominance. Among the earliest known dinosaurs was fossils of this animal have been discovered in what is now Argentina. Eoraptor was relatively small, measuring only about 1 meter in length. Its body was lightly built and it possessed long hind limbs that suggest active movement. Scientists believe it may have had a flexible diet, feeding on small animals and possibly plant material. Another early dinosaur was. This predator lived during the late Triassic and reached lengths of several meters. Herrerasaurus possessed sharp teeth, powerful jaws, and strong limbs. fossils indicate that it was an active hunter capable of pursuing prey across Triassic landscapes. Its anatomy reveals many features associated with later theropod dinosaurs, although its exact evolutionary relationships remain the subject of scientific study. The discovery of has also contributed significantly to understanding dinosaur origins. Found in Brazil, this carnivorous dinosaur displayed characteristics consistent with some of the earliest stages of dinosaur evolution. Its lightweight build and specialized skeletal features provide additional evidence for the emergence of dinosaurs during the late Triassic. These early dinosaurs were part of a broader evolutionary expansion that occurred as environments continued to recover and diversify. Competition among different reptile groups was intense. Dinosaurs were only one component of a complex ecosystem that included crocodile-line archosaurs, large amphibians, early mammals, reptiles of many kinds, insects, and numerous plant species. The climate of the Triassic influenced the evolution of dinosaurs in important ways. Many regions experienced warm temperatures for much of the year. Seasonal rainfall patterns created alternating wet and dry periods. Rivers frequently changed course across floodplains, creating dynamic habitats. Organisms capable of adapting to changing conditions often enjoyed greater evolutionary success. The arrangement of Pangaea also affected the distribution of early dinosaurs. Because the continents were joined together, animals could potentially spread across enormous areas without encountering major ocean barriers. This connectivity allowed evolutionary innovations to spread widely and enabled various groups to expand their geographic ranges. Evidence from fossil discoveries suggests that dinosaurs gradually increased in diversity during the late Triassic. Different lineages began to specialize in various ecological roles. Some focused on hunting small animals, others adapted to feeding on plants. Body shapes, skull structures, and limb proportions became increasingly varied as natural selection acted upon different populations. One major branch of dinosaur evolution gave rise to the theropods. These animals were primarily carnivorous and eventually included famous species such as millions of years later. Another branch led to the sauropodomorphs, whose descendants would include the enormous long-necked dinosaurs of the Jurassic and Cretaceous periods. A third major branch eventually produced the ornithischians, a diverse group containing many plant-eating species. During the earliest stages of dinosaur history, however, these major groups were only beginning to diverge from one another. The differences that would later become so dramatic were still developing. Early dinosaurs generally shared many basic anatomical traits inherited from common ancestors. The fossil record indicates that the emergence of dinosaurs was closely connected to broader environmental and biological changes occurring throughout the Triassic. As ecosystems became more complex, opportunities arose for organisms capable of exploiting new food sources, habitats, and survival strategies. Dinosaurs were among the groups that successfully adapted to these opportunities. Geological activity also influenced evolutionary patterns. Volcanic eruptions, shifting river systems, tectonic movements, and changing climates altered habitats over long periods. These environmental changes created new challenges and opportunities that shaped the direction of evolution. Populations became isolated, adapted to local conditions, and sometimes evolved into entirely new species. The first dinosaurs were not yet the dominant animals that many people imagine when thinking about prehistoric life. Much of the Triassic world remained controlled by other reptilian groups. Nevertheless, dinosaurs possessed characteristics that would eventually allow them to expand and diversify on a remarkable scale. Efficient movement, adaptable body plans, and evolutionary flexibility contributed to their growing success. Toward the end of the Triassic period, another major extinction event affected life on Earth. Many competing reptile groups declined or disappeared. Dinosaurs survived this environmental crisis and emerged into the Jurassic period with greatly reduced competition. This survival would allow them to become the dominant large terrestrial vertebrates for the next 135 million years. At a time when dinosaurs had only begun to appear and Earth's landscapes looked very different from those of today, nearly all of the planet's major landmasses were joined together into a single enormous continent. This giant landmass, known as Pangaea, stretched across a vast portion of Earth's surface and connected regions that are now separated by thousands of kilometers of ocean. Areas that would one day become parts of North America, South America, Africa, Europe, Asia, Antarctica, Australia, and the Indian subcontinent were physically attached to one another. There were no Atlantic Ocean waters dividing Africa from South America, no Indian Ocean separating Africa from India and Australia, and no modern arrangement of continents. Instead, much of Earth's dry land existed as one connected expanse surrounded by a huge global ocean. The existence of Pangaea was not a permanent condition. Earth's surface has never remained fixed. Deep beneath the continents and oceans, powerful geological processes continuously move the rigid plates that form the outer shell of the planet. Although these movements are extremely slow, often occurring at rates of only a few centimeters each year, they become enormously significant when measured across millions of years. Over vast spans of geological time, these forces are capable of moving entire continents across the surface of the Earth. The breakup of Pangaea began during the Triassic period, a time when life on land was recovering from the devastating mass extinction that had occurred at the end of the Permian period. The world was inhabited by a variety of reptiles, early dinosaurs, amphibians, insects, and plants that had adapted to the environmental conditions of the supercontinent. Large deserts occupied many inland regions because enormous distances separated the interior from the influence of ocean moisture. Seasonal changes could be intense, and many parts of the continent experienced hot and dry conditions. While life continued to evolve on the surface, important changes were taking place deep within Earth. Heat generated inside the planet caused material within the mantle to move slowly. These movements transferred energy upward towards the crust. Over time, stress began to build beneath portions of Pangaea. The crust was not able to remain completely stable under these forces. Gradually, fractures started to develop within the supercontinent. At first, these fractures appeared as long zones of weakness stretching across large regions of the landmass. The crust slowly began to pull apart. As the separation continued, deep cracks known as rifts formed. These rifts marked the earliest stages of continental breakup. The process did not occur everywhere at the same time. Different regions experienced rifting at different rates and during different intervals. As the crust stretched, volcanic activity became increasingly common in certain areas. Magma from deep within Earth rose toward the surface through fractures and weak points in the crust. Vast amounts of molten rock erupted across large regions. Some of these eruptions produced extensive lava flows that covered huge areas of land. Layers of volcanic rock accumulated over time, providing geological evidence that scientists still study today. One of the most significant volcanic events associated with the breakup of Pangaea occurred near the boundary between the Triassic and Jurassic periods. Massive eruptions released enormous quantities of lava and gases into the atmosphere. These volcanic events affected global environmental conditions and may have contributed to biological changes occurring during that time. Thick sequences of volcanic rocks formed across areas that would later become parts of North America, South America, Europe, and Africa. As rifting continued, sections of the crust became thinner. The stretching eventually allowed new oceanic crust to form between separating continental blocks. Once this process began, the breakup entered a new stage. Instead of merely developing fractures, portions of Pangaea started to drift apart. New ocean basins gradually appeared between the separating landmasses. One of the earliest major divisions split Pangaea into two large regions. The northern portion became known as Laurasia, while the southern portion became known as Gondwana. Laurasia contained land that would eventually form much of North America, Europe, and Asia. Gondwana included areas that would later become South America, Africa, Antarctica, Australia, Madagascar, and the Indian subcontinent. The separation between Laurasia and Gondwana developed gradually. The Tethys Ocean expanded in some regions, while new zones of oceanic crust formed along spreading centres. As the distance between the northern and southern landmasses increased, marine environments expanded into areas that had previously been part of a continuous continent. The development of new oceans changed global geography. Water began occupying spaces that had once been dry land. Coastlines expanded dramatically. Regions that had previously existed deep within the interior of Pangaea found themselves closer to marine environments. This transformation influenced weather patterns, rainfall distribution, temperature conditions, and ecological systems. The early Atlantic Ocean originated during these stages of continental separation. What is now the eastern coast of North America was once connected directly to northwestern Africa and parts of Europe. As tectonic forces continued pulling the continents apart, a narrow ocean basin formed between them. Initially, this body of water was relatively small compared with the modern Atlantic Ocean. However, continued seafloor spreading gradually widened the basin. New oceanic crust formed continuously along the spreading centre. Molten material rose from beneath the Earth's surface, cooled and solidified to create fresh seafloor. Older crust moved away from the centre as additional material accumulated. This process steadily increased the distance between the separating continents. As millions of years passed, the Atlantic Ocean continued to widen. North America drifted farther from Africa and Europe. South America also began moving away from Africa. The separation occurred slowly but continuously. Geological evidence preserved in rock formations on opposite sides of the Atlantic reveals that these continents were once joined together. Similar rock layers, fossil distributions, and ancient mountain structures can still be traced across continents now separated by vast oceans. The breakup of Gondwana unfolded through multiple stages. Africa and South America remained connected for a considerable period before eventually beginning their separation. The developing South Atlantic Ocean emerged between them as new seafloor formed. As the ocean widened, the coastlines of the two continents gradually assumed shapes resembling those seen today. The separation of Africa and South America had major consequences for ocean circulation. Water could move through newly formed marine pathways, altering patterns of heat transport around the globe. Changes in ocean currents influenced climate systems and affected environmental conditions across many regions. Meanwhile, Antarctica, Australia, and India remained connected within Gondwana for extended periods. Over time, however, tectonic movements continued reshaping these landmasses. India eventually separated and began moving northward across the ocean at a relatively rapid geological pace. This journey would later lead to its collision with Asia, producing major mountain-building events. Australia also gradually separated from Antarctica. As these continents drifted apart, new oceanic passages developed. Antarctica increasingly became isolated from other landmasses. This isolation would later contribute to major climatic changes as ocean currents evolved around the southern polar region. The movement of tectonic plates did not simply alter the positions of continents. It also influenced the formation of mountain ranges. As some regions experienced separation, others experienced collision. The Earth's crust was continuously being reorganized. In some places, rocks were stretched and thinned. In others, they were compressed and uplifted. The changing arrangement of continents affected atmospheric circulation as well. During the existence of Pangaea, the enormous size of the supercontinent had influenced weather patterns on a global scale. Vast interior regions were located far from ocean moisture. As the continent fragmented, coastlines increased, and marine influences reached areas that had previously been isolated from oceanic effects. Rainfall patterns gradually shifted. Some regions became wetter as they moved closer to oceans. Others experienced different seasonal conditions due to changes in latitude and continental configuration. Atmospheric circulation systems adapted to the evolving geography of the planet. The breakup also influenced biological evolution. When continents remained connected, many organisms could spread across extensive regions. As oceans formed between landmasses, populations became increasingly isolated from one another. This isolation created opportunities for separate evolutionary pathways to develop. Plant communities responded to changing climates and geography. Different regions developed distinct environmental conditions that favored particular types of vegetation. Animal populations adapted to local habitats and conditions. Over millions of years, species on different continents often evolved independently, as ocean barriers limited movement between them. Fossils provide important evidence for understanding these processes. Similar fossil species are found on continents now separated by oceans, indicating that those regions were once connected. Scientists have discovered matching fossil records in South America, Africa, Antarctica, India, and Australia. These findings support the reconstruction of ancient continental arrangements and the history of Pangaea's breakup. Geological evidence also comes from ancient mountain belts. Mountain ranges formed before the breakup can often be traced across multiple continents. When the continents are reconstructed into their former positions, these geological features align remarkably well. Rock layers, mineral deposits, and structural patterns further support the understanding that the continents were once joined. As the Jurassic period progressed, continental separation became increasingly pronounced. New ocean basins expanded, coastlines lengthened, and marine ecosystems diversified. The world was becoming progressively less dominated by a single supercontinent and more characterized by multiple distinct continents separated by oceans. During the Cretaceous period, the breakup continued across many regions. South America and Africa moved farther apart. India continued its northward journey. Australia and Antarctica gradually approached separation. Ocean circulation systems became increasingly complex as additional marine connections formed. Sea levels changed throughout these intervals due to multiple geological factors. Expanding mid-ocean ridges influenced ocean basin volumes. Changes in seafloor production affected global marine conditions. Large shallow seas sometimes covered portions of continental interiors, creating extensive marine environments. Volcanic activity remained associated with tectonic processes throughout many stages of continental breakup. Rifting and seafloor spreading generated magma that contributed to the creation of new crust. Volcanic eruptions released gases into the atmosphere and influenced local and regional environments. The movement of continents also altered the distribution of climate zones. Land masses drifted into new latitudes over time. Regions that had once occupied one climatic setting gradually entered different environmental conditions. These shifts influenced ecosystems, vegetation patterns, and animal populations. By the later stages of the breakup process, Pangaea no longer existed as a single continent. Instead, a complex arrangement of separate continental masses occupied the Earth's surface. Although the continents had not yet reached their present locations, the overall transformation from one supercontinent into multiple continents was well underway. The Atlantic Ocean continued expanding throughout this history. Every year, new oceanic crust formed along the mid-Atlantic ridge, increasing the distance between continents on either side. This process remains active today, demonstrating that the breakup of Pangaea was part of a continuing geological evolution, rather than a single event confined to the distant past. Modern continents still carry evidence of their ancient connection. The matching shapes of certain coastlines, similarities in rock formations, shared fossil distributions, and aligned geological structures all preserve records of the time when they formed parts of one immense landmass. These clues have allowed scientists to reconstruct the sequence of events that transformed Pangaea into the world known today. The breakup unfolded through an intricate series of tectonic events extending across tens of millions of years. Rifting, volcanic activity, seafloor spreading, ocean formation, continental drift, climatic changes, ecological transformations, and geological restructuring all formed parts of this long process. Beneath the surface, mantle movements continued driving the slow migration of continents, gradually reshaping the face of Earth across immense spans of geological time. Climate conditions during the Age of Dinosaurs developed over a very long span of Earth history. When the planet passed through major changes in its atmosphere, oceans, land surfaces, and living systems. This time covered a wide interval that began about 230 million years ago and continued until about 66 million years ago. During this entire interval, the physical conditions of Earth were not fixed. They shifted slowly and sometimes rapidly due to internal Earth processes such as volcanic activity, changes in sea levels, movement of continents, and changes in the gases present in the atmosphere. The climate conditions were shaped by the balance between heat coming from the sun, heat trapped by atmospheric gases, and the way oceans and land distributed energy across the planet. The atmosphere during this time contained different proportions of gases compared with later Earth conditions. Carbon dioxide was present in higher concentration for long intervals, especially during periods of intense volcanic activity. This gas influenced how heat was held within the lower atmosphere. Water vapor was also abundant in many regions due to widespread warm surface temperatures and active evaporation from oceans and inland seas. Oxygen levels shifted over time depending on plant activity and geological events. These atmospheric conditions affected rainfall, cloud formation, and seasonal cycles across the planet. At the beginning of this long period, Earth's land masses were joined together in a large configuration. This arrangement influenced how air moved across the surface. Large interior regions of land were far from ocean sources of moisture, which created dry zones in many central areas. Coastal regions received more moisture from nearby seas, while inland regions often experienced long dry intervals. Air movement patterns were influenced by temperature differences between land and sea surfaces. as well as by the rotation of the planet, which created large circulation systems in the atmosphere. Heat distribution across the planet was not even. The equatorial regions received strong and steady solar energy throughout the year. This led to warm surface conditions and high rates of evaporation from shallow seas and coastal waters. The moisture that entered the atmosphere formed clouds and precipitation in many regions. Rainfall patterns were often intense in some zones, especially where warm, moist air rose and cooled in higher layers of the atmosphere. These conditions supported widespread plant growth in suitable environments. In regions closer to the poles, climate conditions were not dominated by permanent ice. Instead, many polar regions experienced periods where forests and diverse plant life existed. The presence of plant material in these regions indicates that temperatures allowed vegetation to survive through long seasonal cycles of light and darkness. During times of extended daylight, plant growth increased, while during long periods of darkness, growth slowed or stopped. These cycles created unique environmental conditions that influenced local ecosystems. Sea levels during many intervals of this time were elevated due to reduced formation of large ice sheets and the expansion of ocean basins caused by geological processes. Large, shallow seas spread across continental areas, creating environments where water was not very deep. These shallow marine environments absorbed solar energy and stored heat within the water column. This contributed to overall warmth in surrounding regions and influenced weather systems above the oceans. Evaporation from these waters supplied large amounts of moisture into the atmosphere. Volcanic activity played a significant role in shaping atmospheric conditions. Large volcanic eruptions released gases such as carbon dioxide, sulfur compounds, and water vapor into the atmosphere. Over long periods, carbon dioxide accumulated and contributed to heat retention in the lower atmosphere. Some volcanic events occurred over extended periods, producing large volumes of lava that spread across land surfaces. These events altered atmospheric composition and affected temperature patterns across wide regions of the planet. During intervals of increased volcanic activity, atmospheric particles were also released into the air. These particles affected sunlight reaching the surface for shorter periods of time, creating variations in surface temperature. After such particles settled, the influence of greenhouse gases remained, maintaining elevated levels of heat in the atmosphere. These cycles contributed to changes in rainfall distribution and cloud formation patterns. Ocean circulation systems were strongly influenced by continental positions and the shape of ocean basins. Warm ocean currents transported heat from equatorial regions toward higher latitudes. Cold water currents moved in opposite directions, creating circulation loops within ocean systems. These movements affected temperature distribution in coastal areas and influenced the formation of weather systems over land. Ocean water also stored large amounts of heat, which affected climate stability over long time spans. The chemistry of ocean water changed over time due to interactions with volcanic gases, river inflow, and biological activity. Carbon dioxide dissolved in seawater affected acidity levels, which influenced marine life and the formation of calcium-based structures. Warm, shallow seas supported extensive marine ecosystems, which in turn influenced the exchange of gases between the ocean and atmosphere. These exchanges played a role in regulating atmospheric conditions. Rainfall patterns during this time were influenced by seasonal shifts, atmospheric circulation, and the distribution of land and sea. Some regions experienced strong seasonal wet and dry cycles due to shifting wind patterns. Monsoon-like systems developed in areas where land heating and ocean moisture interacted strongly. During warm seasons, moist air moved over land and produced heavy rainfall. During cooler seasons, dry air dominated, reducing precipitation levels. Desert regions existed in areas where moisture was limited by atmospheric circulation patterns. These regions received low levels of precipitation over long periods of time. Despite dry conditions, occasional rainfall events occurred, which briefly supported plant and animal activity. Dust and sand were transported by wind systems across these dry zones, affecting soil composition and surface conditions. The types of plants present during this period influenced climate conditions through their interactions with the atmosphere. Large forests of conifers, cycads, ferns, and other plant groups covered many land areas. These plants absorbed carbon dioxide during growth and released oxygen into the atmosphere. Dense vegetation in some regions increased local humidity through transpiration, which released water vapor into the air. This process contributed to cloud formation and local rainfall. In swampy regions, plant material accumulated in waterlogged soils. These environments had limited oxygen in the soil, which slowed the decomposition of organic material. The presence of such wetlands influenced local humidity levels and affected nearby climate conditions. Large amounts of plant growth in these regions contributed to changes in atmospheric gas composition over long time intervals. The movement of continents across Earth's surface changed climate conditions gradually. As landmasses shifted position, they moved through different latitude zones. This altered exposure to solar energy and changed the flow of ocean currents around them. When continents were located closer to polar regions, they experienced long seasonal cycles of light and darkness. When positioned closer to equatorial regions, they experienced more constant warmth and rainfall patterns. Mountain formation events also influenced atmospheric circulation. When large mountain ranges formed, they altered wind flow patterns and redirected moisture movement. Air rising over elevated terrain cooled and released precipitation on one side of the mountain regions. The other side often experienced reduced moisture levels. These processes contributed to the development of dry and wet zones across continents. During certain intervals, Earth experienced prolonged periods of elevated global temperatures. These periods were associated with increased volcanic activity and higher atmospheric carbon dioxide levels. During such times, ice was largely absent from the planet. Oceans expanded over continental margins, and shallow marine environments became widespread. Atmospheric moisture increased, leading to frequent cloud formation in many regions. Storm systems developed over warm ocean surfaces where evaporation was intense. Warm air rose rapidly, forming large cloud systems that produced heavy rainfall and strong wind patterns. These storms influenced coastal environments and contributed to the redistribution of heat and moisture across regions. Thunderstorm activity was common in areas with strong heating and abundant moisture supply. Seasonal cycles existed due to the tilt of Earth's axis. These cycles affected the distribution of sunlight throughout the year in different regions. In higher latitude areas, seasonal changes were more pronounced, leading to periods of continuous daylight followed by extended darkness. These cycles influenced plant growth patterns and animal behavior, which in turn affected local environmental conditions. Atmospheric oxygen levels changed slowly over time due to biological activity and geological processes. Plant growth contributed to oxygen production, while decomposition and combustion processes reduced oxygen levels. These changes influenced the energy available in ecosystems and affected the development of large land animals. Oxygen distribution in the atmosphere also influenced fire activity in dry regions, where plant material could ignite under suitable conditions. Fire events occurred naturally in some environments due to lightning strikes and dry vegetation. These fires influenced plant distribution and nutrient cycling in soils. After fire events, new plant growth often occurred in affected areas, gradually restoring vegetation cover. These cycles influenced local climate conditions by changing surface reflectivity and moisture retention. Dust and aerosol particles in the atmosphere influenced cloud formation processes. These particles acted as surfaces where water vapor could condense, forming cloud droplets. The presence of such particles varied depending on volcanic activity, wind patterns, and surface conditions. Changes in cloud formation affected rainfall distribution and temperature regulation in the atmosphere. During long intervals, Earth's climate system maintained a generally warm and humid state in many regions. However, variations existed across different time periods due to geological and atmospheric changes. Some intervals experienced higher rainfall and dense vegetation coverage, while others experienced increased dryness in continental interiors. These variations were part of ongoing shifts in Earth's internal and surface systems. The interaction between oceans and atmosphere played a central role in regulating climate conditions. Heat exchange between ocean water and air influenced weather systems and temperature distribution. Ocean evaporation supplied moisture that supported cloud formation, while precipitation returned water to land and sea surfaces. This continuous movement of water through different states maintained atmospheric moisture levels. Carbon cycling between living organisms, oceans, and the atmosphere influenced long-term climate stability. Carbon dioxide was absorbed by plants and marine organisms and later released through decay and volcanic activity. This cycle affected atmospheric composition over extended periods. The balance between carbon storage and release shaped temperature conditions across geological time. Some regions experienced long-lasting wet environments, where lakes and inland seas remained stable over extended periods. These water bodies supported diverse ecosystems and influenced surrounding atmospheric moisture. Evaporation from these water bodies contributed to local cloud formation and rainfall. The presence of large inland water systems affected regional temperature stability. In areas with limited water supply, surface conditions were dominated by dry soils and sparse vegetation. These regions experienced strong temperature changes between day and night due to low moisture content in the ground. Wind systems transported dust and fine particles across these regions, shaping surface deposits and influencing atmospheric clarity. The distribution of climate zones shifted gradually over millions of years due to tectonic movement and atmospheric changes. Regions that were once humid could become dry over long periods, while dry regions could later receive increased moisture. These transitions were driven by changes in land position, ocean circulation, and atmospheric gas composition. Solar energy input remained a constant factor, influencing climate conditions throughout this entire period. The way this energy was distributed across the planet depended on atmospheric composition, surface reflectivity, and cloud coverage. Changes in any of these factors influenced temperature patterns and weather systems across different regions. The long duration of this time allowed for continuous interaction between geological processes and atmospheric conditions. Volcanic eruptions, continental movement, ocean circulation, and biological activity all contributed to ongoing changes in climate structure. These processes operated together across millions of years, shaping the environmental conditions under which dinosaurs lived across the planet. The earliest forms of dinosaurs appeared during a long stretch of Earth's history, when land ecosystems were slowly changing and many reptile groups were spreading across different regions of the world. These early dinosaur groups did not appear suddenly in a fully developed state. They emerged gradually from earlier reptile relatives that already lived on land. Over long periods, small changes in body structure, movement, feeding habits, and bone arrangement led to the rise of animals that would later be recognized as dinosaurs. The earliest dinosaur groups were made up of several lineages that began to separate in form and function, and these lineages laid the foundation for all later dinosaur life across millions of years. During the time when early dinosaurs first appeared, many land animals were part of a broader group of reptiles that shared the environment. Among these reptiles were forms that moved on 4 legs and forms that could move on 2 legs for part of their activity. The earliest dinosaur ancestors came from this diverse reptile background. Over time, certain groups developed body features that allowed more efficient movement on land, especially when moving with an upright posture where the legs were positioned more directly under the body. This posture allowed movement that required less dragging of the body across the ground. These changes formed part of the early development of dinosaur groups. The earliest dinosaur forms belonged to several major branches that later became well known in the fossil record. One of these branches included early theropod dinosaurs. These were mostly animals that walked on 2 legs and had bodies built for active movement. Early theropod forms had long hind limbs that supported most of their body weight. Their front limbs were generally smaller and used in different ways depending on the species. Their skulls were shaped with openings that reduced bone weight while still maintaining strength. Teeth in early theropods were often shaped for gripping and cutting food materials. These early theropods were among the first dinosaur groups to show clear signs of active movement on land with strong limb coordination. Another early dinosaur branch included sauropodomorph forms. These early animals were also adapted for land movement and were part of the first stages that later led to very large, long-necked dinosaurs. The earliest sauropodomorphs had bodies that were still developing the full structure seen in later forms. Their necks were often moderately long and their tails extended behind the body to help with balance. They were able to move on both 2 legs and 4 legs depending on their activity and body structure. Their teeth were often small and shaped for feeding on plant material available in their environment. The early sauropodomorph forms were part of a gradual change in feeding habits among reptiles living on land. The third major early dinosaur branch included ornithischian forms. These early animals were part of a group that later produced many plant-eating dinosaurs with varied body structures. Early ornithischians had hips that were arranged in a way that supported efficient movement on land. Their teeth were adapted for processing plant material, and their jaws allowed repeated chewing motions. Their body size in early forms was generally moderate, and their limbs supported steady movement across land surfaces. The early ornithischian forms developed body features that would later expand into many different types of plant-eating dinosaurs across various environments. Before these 3 major branches fully developed, there were early dinosaur relatives known as dinosauromorphs. These were close to dinosaurs but not fully classified as true dinosaurs in later definitions. Dinosauromorphs had light body structures and long limbs. Their movement patterns suggested increasing adaptation to upright walking. These early forms played an important role in the transition from earlier reptiles to full dinosaur groups. Their fossils show gradual changes in bone structure, especially in the pelvis and legs, which became more suited for supporting body weight directly above the limbs. As early dinosaur groups continued to develop, the structure of their skeletons became more specialized. The spine became more stable in connection with the pelvis, allowing stronger support for movement. The hips of early dinosaurs developed into forms that allowed the hind limbs to support the full body weight more effectively. This change was important in the development of upright walking, where the legs were placed under the body rather than extended outward. This posture allowed more efficient movement across land environments. The skulls of early dinosaur groups also developed changes. Openings in the skull reduced overall weight while maintaining strength in areas needed for feeding. The jaw muscles attached in ways that allowed stronger biting force in some groups, especially in theropods. In sauropodomorph and ornithischian early forms, the skull structure allowed feeding on plant materials in different ways. The arrangement of teeth and jaw movement became more specialized in each group over time, allowing early dinosaurs to use available food sources more effectively. The limbs of early dinosaur groups showed distinct patterns of development. Hind limbs were generally stronger and longer than forelimbs in many early forms. This pattern supported movement on land with a focus on forward motion. In theropod early forms, the hind limbs carried most of the body weight, while the forelimbs became lighter and more flexible. In sauropodomorph early forms, both sets of limbs were used for movement, with gradual changes leading toward stronger hind limb support in some later species. In ornithischian early forms, limb structures supported steady movement and balance during feeding and travel. Early dinosaur groups also showed differences in body covering and skin structure. Fossil evidence suggests that skin textures varied among early forms. Some early theropod relatives show signs that later evolved into structures related to feathers, although early forms had simple coverings. These structures were not yet developed into complex forms, but represented early stages of body surface changes. Other early dinosaur groups had different skin textures that supported protection and movement across rough ground surfaces. The environments where early dinosaur groups lived included land areas, with changing vegetation and shifting climate conditions. These environments supported a wide range of plant types including ferns, cycads, and other early plant groups. Early dinosaur groups interacted with these plant resources in different ways depending on their feeding structures. Herbivorous early dinosaurs consumed plant material using teeth and jaw movements adapted to available vegetation. Carnivorous early dinosaurs consumed animal prey, including smaller reptiles and other available organisms. The early development of dinosaur groups involved changes in growth patterns. Juvenile forms often showed different body proportions compared to adult forms. Limb length, skull shape, and body size changed as individuals grew. Growth rates varied among different early dinosaur groups depending on species and environmental conditions. These growth patterns contributed to the diversity seen in later dinosaur evolution. Early theropod forms included several lineages that displayed variations in size and movement. Some early theropods were small and light, adapted for fast movement across land surfaces. Others were larger and had stronger skull structures for feeding on a range of prey. The development of sharp teeth in many theropod groups supported feeding habits that involved tearing flesh and processing smaller animals. The arrangement of bones in the legs supported upright walking and running movement patterns. Early sauropodomorph forms showed gradual changes in neck length and body size. The neck structure allowed access to plant material at different heights. The tail structure supported balance during movement. The limbs were structured to support increasing body weight over time in later forms. Early members of this group did not yet show the extreme body sizes seen in later descendants, but they displayed early adaptations that would lead in that direction over long periods. Early ornithischian forms developed jaw structures that allowed more efficient processing of plant material. Teeth were arranged in ways that supported repeated chewing actions. The lower jaw moved in patterns that allowed grinding of plant material. These early adaptations allowed ornithischian groups to make use of different plant resources available in their environment. The hips and pelvis structure supported stable movement while feeding and traveling. The fossil record of early dinosaur groups shows that their distribution across land areas expanded over time. Fossils of early forms have been found in different parts of the world, indicating that these animals spread across connected land environments. Their spread was influenced by land connections that existed during that time period, allowing movement across large regions without major barriers such as wide oceans. Early dinosaur groups also interacted with other reptile groups that shared their environment. These interactions included competition for food resources and space. Some early reptile groups remained dominant in certain regions, while early dinosaurs began to occupy new ecological roles. Over time, dinosaur groups expanded their presence in many environments, leading to increased diversity in body forms and feeding strategies. The structure of early dinosaur bones shows evidence of strong internal support systems. Bone tissues were arranged to provide strength while reducing unnecessary weight. This allowed efficient movement and energy use during activity. The internal bone structure also supported growth and repair over time, allowing individuals to reach maturity under different environmental conditions. Early dinosaur groups also developed respiratory systems that supported active movement. Air passages within the body allowed airflow through the lungs in a way that supported sustained activity. This system contributed to energy efficiency during movement and feeding. The arrangement of internal organs supported the upright posture that became a key feature of dinosaur groups. The development of early dinosaur groups involved gradual separation into distinct lineages. Each lineage developed its own set of physical features and feeding strategies. These differences became more pronounced over time as populations adapted to different environments. The separation of theropod, sauropodomorph, and ornithischian groups marked a major stage in dinosaur development. Early dinosaur trackways found in rock layers provide evidence of movement patterns. These trackways show sequences of footprints that indicate walking direction, speed, and group movement in some cases. The spacing of footprints shows differences in limb length and walking style among early dinosaur forms. These trackways also indicate that early dinosaurs moved across different types of ground surfaces, including soft sediment and firmer ground. The early evolution of dinosaur groups also included changes in reproductive behavior. Eggs were laid in nests on land, and these nests were placed in locations that provided protection and suitable environmental conditions. The structure of eggs varied among different groups, and the arrangement of nesting sites suggests different reproductive strategies among early dinosaurs. As early dinosaur groups continued to develop, their diversity increased across land environments. Different groups adapted to different ecological roles, including feeding on plants, hunting smaller animals, and moving across varied terrain. These adaptations led to a wide range of body structures within early dinosaur forms. The early stages of dinosaur evolution represent a period of gradual biological change across many generations. Each group developed features that supported survival in specific environments. The interactions between body structure, movement, feeding and environmental conditions shaped the development of early dinosaur groups across long periods of Earth's history, with ongoing changes continuing across successive generations without final resolution in their developmental path. The appearance and long development of plant-eating dinosaurs took place across a very long stretch of geological time, when land environments were undergoing constant changes in structure, climate, and biological life forms. These dinosaurs formed a major part of land-animal communities, and their presence shaped the way many ecosystems functioned. Their development began after early reptile groups had already established themselves on land and had started to diversify into many different forms with different feeding habits, movement styles, and body structures. The transition toward plant-eating lifestyles involved gradual changes in teeth, jaws, digestive systems, neck length, body size, and limb structure, all of which happened across many generations of species. During the earliest stages of dinosaur development, many reptile groups that lived on land were still mainly feeding on insects, small animals, and a mix of plant material when available. Over time, certain lineages began to consume more plant material, as plants became more widespread and more varied in form. This change in feeding behavior was linked to the availability of vegetation that grew in different heights and densities across land surfaces. As plant life expanded in different directions, some reptiles adapted to feeding on stems, leaves, and other plant structures. These early feeding habits did not immediately produce fully specialized plant-eating dinosaurs, but they set the stage for gradual biological change. As time continued, the body structures of some dinosaur lineages began to show clear features related to plant consumption. Teeth became shaped in ways that allowed cutting, grinding, and breaking plant tissue. Jaw movement became more suited to repeated chewing actions. In some groups, teeth were arranged in rows that allowed continuous replacement as older teeth wore down from constant use. This was important because plant material can cause heavy wear on teeth, especially when consumed in large amounts over long periods. The ability to replace teeth helped maintain feeding efficiency throughout life. The skull structure of these dinosaurs also changed over time. Certain skull regions became wider to allow more space for muscle attachment. Stronger jaw muscles allowed more forceful movement during feeding. The arrangement of bones in the skull became more supportive of sustained chewing activity. Some species developed beak-like structures at the front of the mouth which assisted in cropping plant material from stems and branches. These beak structures were often made of keratin covering bone and were useful for cutting vegetation before it was processed by the teeth further back in the mouth. The neck region in many plant-eating dinosaurs developed additional flexibility and length in some lineages. This allowed access to vegetation located at different heights from the ground. Feeding at ground level, mid-level vegetation, and higher plant structures required different movement patterns of the neck. The development of additional vertebrae in some groups supported this range of motion. Muscles along the neck also adapted to support the weight and movement of the head during feeding activities that lasted long periods. The body structure of plant-eating dinosaurs often included a large digestive system. Plant material is difficult to break down because it contains fibrous components. To process this material effectively, internal digestive chambers became larger in many species. Some dinosaurs developed expanded gut regions that allowed food to remain inside the body for extended periods, giving time for breakdown and absorption of nutrients. This digestive adaptation was necessary for sustaining energy levels from plant-based diets. The limbs of plant-eating dinosaurs also showed changes related to stability and movement. Many species developed strong, weight-supporting limbs that allowed them to stand for long periods while feeding. Some walked on 4 limbs, which helped distribute body weight evenly across the ground. Others used 2 limbs for movement, while the remaining limbs supported feeding posture or balance during motion. The arrangement of bones in the limbs became structured in ways that supported both slow movement and stable standing positions during feeding. The skin covering of plant-eating dinosaurs varied across different groups. In many cases, the skin developed protective structures that helped reduce damage from environmental exposure and plant material. Some species developed bony plates or thickened skin regions that covered parts of the body, such as the back, neck, and tail. These structures provided physical protection during interactions with plant environments that contained dense vegetation. Plant-eating dinosaurs appeared in a wide range of environments. Some lived in forested regions where plant life was dense and layered at different heights. Others lived in open land areas where vegetation was spread across wide spaces. Some inhabited regions near water sources where plant growth was supported by moisture. The distribution of these dinosaurs across different environments shows that plant-eating behavior was not limited to a single habitat type, but was present in many ecological settings. The development of plant-eating dinosaurs was closely linked to the evolution of plants themselves. During early stages of land-plant development, vegetation was relatively simple in structure. Over time, plants became more complex, developing leaves, stems, and branching systems that increased the amount of available plant material. This increase in plant structure provided more feeding opportunities for herbivorous dinosaurs. As plant diversity increased, dinosaur feeding adaptations also diversified to match available plant resources. Some plant-eating dinosaur groups developed specialized feeding methods. Certain species used rows of teeth that functioned in continuous grinding motions. Others used simple cropping actions, followed by minimal chewing. Some species had teeth shaped for slicing through tough plant fibers. These differences in feeding methods allowed multiple plant-eating groups to exist in the same environments while using different parts of plant resources. Growth patterns in plant-eating dinosaurs also changed in relation to their feeding habits. Many species grew continuously throughout early stages of life, increasing in body size as they consumed large amounts of vegetation. Growth was supported by efficient energy use from plant material. Bone structure in growing individuals showed signs of rapid development in certain stages, followed by slower growth phases as maturity was reached. This pattern allowed young individuals to reach sizes that supported survival in environments where feeding competition existed among many plant consumers. Reproduction in plant-eating dinosaurs involved laying eggs in nesting areas that were often located in protected environments. Some species laid eggs in clusters, which allowed multiple offspring to develop in close proximity. The nesting behavior was linked to environmental conditions and plant availability. In some cases, nesting sites were chosen near areas with abundant vegetation, which supported feeding needs of newly hatched individuals. The early life stages of plant-eating dinosaurs involved gradual development of feeding abilities. Newly hatched individuals often had simpler teeth and smaller body sizes. As they grew, their teeth were replaced and reshaped to match adult feeding behavior. This developmental process allowed young individuals to transition from simple feeding to more complex plant consumption over time. Social behavior in plant-eating dinosaurs varied across different groups. Some species moved in organized group structures where individuals traveled together while feeding. This behavior influenced movement patterns across land areas where vegetation was available in patches. Group movement also affected how plant material was consumed across regions, as feeding activity was distributed among multiple individuals. Communication among plant-eating dinosaurs likely involved body movement, sound production, and visual signals. These communication methods supported coordination during movement and feeding activities. Certain physical structures such as crests, horns, or body shapes may have played roles in visual recognition among individuals of the same species. The development of sensory systems in plant-eating dinosaurs also supported feeding behavior. Vision systems allowed detection of plant structures at different distances. Smell systems may have helped identify areas with high plant concentration. These sensory abilities supported navigation through environments where plant resources were spread across large areas. Over time, plant-eating dinosaurs became a major part of land ecosystems. Their feeding activities influenced plant distribution, plant growth patterns, and the structure of vegetation communities. Continuous feeding on plant material affected how plant groups regenerated and spread across land surfaces. This interaction between plant eaters and plant life formed a long-term biological relationship that influenced the structure of ecosystems. Different lineages of plant-eating dinosaurs developed unique anatomical structures suited to their feeding environments. Some had wide bodies that supported large digestive systems. Others had elongated neck structures that allowed feeding from higher vegetation layers. Some developed strong tails that supported balance during movement or feeding posture. These variations in body structure reflect adaptation to different plant consumption strategies. The fossil record of plant-eating dinosaurs shows gradual changes in bone structure over long periods of time. Early forms had simpler, skeletal features, while later forms developed more complex structures related to feeding and movement. Teeth fossils show repeated patterns of wear, replacement, and reshaping, indicating continuous use in processing plant material. Plant-eating dinosaurs also showed variation in growth duration. Some species reached maturity over extended periods, while others developed more rapidly depending on environmental conditions and food availability. Growth rates were influenced by factors such as plant abundance, climate conditions, and habitat structure. Environmental changes over time also influenced the development of plant-eating dinosaurs. Shifts in temperature, rainfall, and land structure affected plant distribution. As plant communities changed, plant-eating dinosaurs adapted their feeding habits and movement patterns to match available resources. This led to continued biological change across many generations. Some plant-eating dinosaurs developed adaptations for processing particularly tough plant materials. These adaptations included specialized teeth structures, stronger jaw muscles, and reinforced skull regions. These features allowed access to plant resources that were not easily consumed by other herbivores. The digestive systems of many plant-eating dinosaurs likely contained regions where plant material was broken down over extended periods. This internal processing allowed extraction of nutrients from fibrous plant matter. The efficiency of digestion varied across different groups, depending on internal structure and feeding habits. As plant-eating dinosaurs continued to diversify, their presence became widespread across land environments. Their adaptations allowed them to occupy many ecological roles related to plant consumption. Different species developed feeding strategies that matched their physical structures and environmental conditions. The continued development of plant-eating dinosaurs involved constant biological changes across generations. Teeth, jaws, necks, limbs, and digestive systems all underwent gradual modification in response to feeding needs and environmental conditions. These changes occurred over long periods of time through successive populations of species. Plant-eating dinosaurs maintained their role within ecosystems through continuous interaction with plant life and land environments. Their feeding activities, growth patterns, and movement behaviors remained closely connected to the distribution and availability of vegetation across different regions. The development of predatory dinosaurs took place over a very long span of Earth history, when life on land was changing slowly through many geological periods. These animals were part of a larger group called theropods, which were bipedal dinosaurs that walked on two legs and mainly fed on other animals. Their origin can be traced back to the late Triassic time, when the world was already filled with many different reptiles, early dinosaurs, and other ancient creatures that shared land, water, and air environments. During this early stage, ecosystems were unstable and changing, and many groups of reptiles were competing for survival in different habitats across the planet. The earliest forms that would later develop into predatory dinosaurs appeared during a time when Earth was arranged into a single large landmass. The climate in many regions was generally warm, and dry areas existed alongside wetter zones. Vegetation was present in the form of ferns, cycads, and other seed plants that did not produce flowers. In this environment, small bipedal reptiles began to show body structures that allowed them to move quickly on land. These early forms had long tails, lightweight bodies, and legs positioned under their hips, which allowed upright movement. These traits became important in later predatory dinosaurs. As time moved into the later part of the Triassic period, more advanced early dinosaurs appeared. Some of these early theropod ancestors developed sharper teeth that were curved and designed for tearing flesh. Their skulls became lighter in structure, and openings in the skull reduced weight while maintaining strength. The neck became flexible, allowing movement in many directions, and the arms remained relatively small but useful for balance and holding prey. These early predators were not large animals in most cases, and many of them depended on speed and quick movement to catch smaller reptiles and early mammal relatives. The growth of predatory dinosaurs continued into the Jurassic period, which brought major changes in ecosystems. By this time, many plant-eating dinosaurs had grown larger and more diverse, creating a steady source of food for carnivorous species. Predatory dinosaurs began to diversify into many forms. Some became fast runners with slender bodies, while others developed stronger jaws and heavier skulls. The structure of their teeth also changed in many lineages, with some developing blade-like teeth that could cut through flesh more efficiently. The bones of these animals show that air-filled spaces were present in many parts of the skeleton, reducing weight while maintaining strength. During this time, the muscles of predatory dinosaurs became more developed in the legs and tail. The tail helped with balance during movement, especially when running or turning quickly. The hind limbs carried most of the body weight, while the front limbs varied in size depending on the group. In some species, the arms were short but still functional for holding prey or stabilizing the body during movement. The hands often had curved claws that could grip or tear flesh. The sensory abilities of these animals also developed further. The skull structure shows that vision was an important sense, with eye placement allowing detection of movement across wide areas. The sense of smell became strong in many species, supported by enlarged nasal regions and brain structures connected to olfactory processing. Hearing ability also improved in some groups, allowing detection of sounds from other animals in the environment. These sensory developments supported survival in environments where many predators and prey animals existed together. As the Jurassic period continued, predatory dinosaurs began to occupy many ecological roles. Some lived in forested regions where they moved between trees and open areas. Others lived in dry environments where they followed herds of plant-eating dinosaurs. There were also smaller predatory species that hunted insects, small reptiles, and early mammals. These smaller predators had delicate but sharp teeth and flexible bodies that allowed them to move through narrow spaces and dense vegetation. The skeletal structure of these animals shows that bone growth patterns varied depending on species and environment. Growth rings in bones indicate that some individuals grew steadily throughout their lives, while others experienced changes in growth speed depending on food availability and environmental conditions. The bones also show signs of healing after injury, which suggests that these animals could survive physical damage and continue living in their environments. As time moved into the later Jurassic period, some predatory dinosaurs reached very large sizes. These large carnivores had massive skulls filled with strong jaw muscles. Their teeth were thick and serrated, allowing them to grip and tear large pieces of flesh. The neck muscles were powerful, supporting the head during feeding and movement. Despite their large size, these animals still relied on movement and coordination to capture prey, and their bodies were structured to support weight while maintaining mobility. The skin covering of predatory dinosaurs is not fully known in all cases, but evidence from fossil impressions shows that some had scales covering most of their bodies. In some species, small feather-like structures appeared, especially in smaller theropods. These feathers may have had different functions depending on the species, including insulation and display. The presence of feathers in some predatory dinosaurs indicates that the development of body covering was not uniform across all groups. During the transition into the Cretaceous period, predatory dinosaurs continued to diversify further. The environment on Earth changed with shifting continents, rising and falling sea levels, and changes in plant life. Flowering plants began to appear and spread, changing the structure of ecosystems. Predatory dinosaurs adapted to these changes in many ways. Some developed stronger jaws to handle different types of prey, while others became more specialized hunters of particular animals. In the early part of the Cretaceous period, small and medium-sized predatory dinosaurs became widespread in many regions. These animals often had highly flexible bodies and fast movement abilities. Their teeth varied in shape depending on diet, and some species had teeth suited for gripping small prey, while others had teeth adapted for slicing flesh. The limbs of these animals often showed adaptations for speed, with long bones in the legs and strong muscle attachment points. As the Cretaceous period progressed, some predatory dinosaurs evolved into very large forms that dominated land ecosystems. These large carnivores had skulls that were heavily built and capable of delivering strong bites. Their necks were muscular and supported large heads. The vertebrae in their backbone were reinforced to handle stress during movement and feeding. Even with their large size, they remained active predators that relied on movement and sensory awareness. At the same time, smaller predatory dinosaurs continued to exist and diversify. Some of these smaller forms developed specialized hunting strategies based on speed and agility. Their bones show adaptations for rapid acceleration and quick direction changes. The structure of their feet, with curved claws and flexible joints, allowed them to grip surfaces and maintain stability during movement. Their arms in some species became more flexible, allowing them to handle prey in different ways. The brain structure of predatory dinosaurs also shows gradual development over time. Fossil evidence from skulls indicates that regions of the brain associated with vision, smell, and coordination were well developed. This allowed these animals to process information from their environment efficiently. The balance system in the inner ear also became important for movement control, especially for bipedal species that relied on running. Reproductive behavior in predatory dinosaurs is not fully known, but fossil evidence shows that they laid eggs. Nesting sites discovered in different regions show that some species cared for their eggs in organized ways. The arrangement of eggs in nests and the presence of nesting materials indicate that reproduction involved specific behaviors that supported the survival of offspring. Young predatory dinosaurs likely grew through stages where body proportions changed as they matured, with limbs and skulls developing at different rates. The interaction between predatory dinosaurs and other animals shaped their development over time. Herbivorous dinosaurs provided a constant food source which influenced the evolution of hunting strategies. Predators developed different methods of capturing prey depending on size, speed, and environment. Some relied on ambush behavior, waiting in hidden areas before attacking. Others used active pursuit, following prey over long distances until capture was possible. These behaviors are supported by fossil evidence of trackways and body structures. The structure of teeth in predatory dinosaurs continued to change through time. Some species developed teeth that were replaced frequently throughout their lives, ensuring that damaged teeth could be replaced. The arrangement of teeth in the jaw allowed efficient biting and tearing, and in some species, the jaw could withstand high levels of force. The jaw joint structure allowed movement that increased the effectiveness of feeding. Muscle attachment points on bones show that predatory dinosaurs had strong muscular systems. The muscles of the neck, jaw, and legs were especially important for survival. These muscles allowed movement, feeding, and stability during motion. The tail muscles also played an important role in balancing the body during movement and changing direction. The nervous system of predatory dinosaurs can be studied through brain cavity impressions in fossils. These impressions show that coordination and sensory processing were important functions. The development of nerve pathways allowed rapid response to environmental stimuli, which was necessary for hunting and avoiding threats. The integration of sensory input from eyes, nose, and ears allowed these animals to respond effectively to their surroundings. Environmental changes during the Cretaceous period influenced the distribution of predatory dinosaurs. Shifts in temperature, rainfall, and plant distribution changed the availability of prey in different regions. As a result, predatory dinosaurs occupied a wide range of habitats, including forests, plains, river valleys, and coastal regions. Each habitat supported different types of prey and required different survival strategies. Some predatory dinosaurs developed physical features that supported movement in specific environments. For example, species living in dense vegetation often had more flexible bodies and shorter limbs, while those in open areas had longer limbs adapted for sustained movement. The differences in skeletal structure reflect adaptation to different ecological conditions without forming conclusions about dominance or hierarchy. Fossil evidence of predatory dinosaurs is found in many parts of the world, including bones, teeth, footprints, and occasionally skin impressions. These fossils provide information about their physical structure and movement. Trackways show patterns of walking and running, indicating how these animals moved across different surfaces. Some trackways show single individuals, while others show multiple animals moving in the same direction. The extinction of many predatory dinosaur groups occurred after major environmental changes at the end of the Cretaceous period. These changes affected ecosystems across the planet, altering food availability and habitat structure. The fossil record shows a reduction in diversity after this period, with many species no longer appearing in later geological layers. The final stages of predatory dinosaur existence are recorded in rock layers that mark this transition in Earth history. The evolution of giant sauropods took place over a long span of Earth history, when large reptile groups slowly changed in body structure, feeding habits, and movement patterns across many environments on land. These animals belong to a major group of dinosaurs known for long necks, long tails, column-shaped legs, and bodies that supported large internal systems for digestion and growth. Their origin can be traced back to early dinosaur forms that appeared during the time when Earth's land was arranged in connected landmasses, and ecosystems were still developing stable plant communities and diverse herbivore populations. Early ancestors of sauropods appeared during a time around 230 million years ago in the late Triassic period. These early forms were not yet giant in body size. They were small to medium in length with lighter bodies and more flexible movement. Their skeletal structure showed early features that would later become important for sauropod development, including elongated neck vertebrae and changes in limb posture. The limbs began to support weight in a more vertical position, which helped in holding the body above the ground with greater stability. Their teeth were shaped for eating plant material, and their jaws were capable of stripping vegetation from low and medium heights. During this early stage, the environment contained large areas of vegetation made up of ferns, seed plants, and early gymnosperms. These plants formed dense growths in some regions, allowing herbivorous dinosaurs to feed in a continuous way. Early sauropod relatives moved through these environments while gathering plant material that was not highly tough or heavily fibrous. Their digestive systems developed gradually to handle large amounts of plant intake, which supported steady body growth over time. As time continued into the early Jurassic period, around 210 million years ago, changes in climate and plant distribution influenced the development of sauropod lineages. Plant life became more varied, and some regions developed taller vegetation structures. This led to evolutionary changes in feeding reach and neck length. The neck bones of early sauropods began to elongate further, with additional vertebrae development and lighter internal bone structures. Air-filled spaces inside the bones increased, which reduced overall skeletal weight while maintaining strength for support. The limbs of these animals became more column-like, with bones arranged in a straight vertical alignment under the body. This structure allowed support of heavier internal organs and larger digestive systems. The feet developed broad contact surfaces with the ground, spreading weight across a wider area during movement. These changes made it possible for the animals to support increased body mass while moving across forested and open environments. The digestive system of early sauropods became more complex as plant material intake increased. Large fermentation chambers developed in the gut, allowing plant fibers to break down over long periods. This internal process supported energy release from plant material that was otherwise difficult to digest. Feeding behavior involved continuous intake of vegetation, with the neck allowing access to food sources across different vertical ranges within plant communities. By the Middle Jurassic period, around 170 million years ago, sauropods had developed into forms with significantly increased body dimensions. Their skeletons showed more specialized adaptations for supporting large mass. The vertebrae of the neck and tail became highly structured with internal cavities, reducing bone density while maintaining strength. Muscle attachment points along the spine became more developed, supporting movement of the neck and tail during feeding and balance adjustment. The tail of sauropods played an important role in body balance. As the neck length increased, the tail extended and developed strong muscular control. This helped maintain stability when the animal shifted its feeding position or moved across uneven ground surfaces. The nervous system also expanded in complexity, allowing coordination of movement across a long body structure. During this time, sauropods occupied a wide range of environments, including floodplains, forest margins, and open vegetated regions. Water availability influenced plant growth, and seasonal changes affected feeding patterns. Sauropods adapted by moving through areas where vegetation was abundant, maintaining steady feeding activity to support continuous growth. Their reproductive cycles involved laying eggs in nests placed in soil or covered vegetation areas. Hatchlings were small and grew rapidly in early life stages, relying on plant intake soon after emerging. In the later Jurassic period, around 150 million years ago, sauropod diversity increased further. Different groups developed variations in neck length, skull shape, and tooth arrangement. Some forms developed narrow teeth suited for stripping leaves, while others developed broader teeth for processing a wider range of plant material. Skull structures became lighter, with openings in the bone reducing weight while maintaining strength for feeding movements. The respiratory system of sauropods developed a structure that included air sacs connected to lung spaces. This system allowed airflow through the body in a continuous pattern, supporting oxygen exchange across a large body volume. The presence of air sacs also influenced bone structure, as many bones became hollow with internal air spaces. This adaptation reduced overall skeletal mass while allowing structural integrity for movement and support. The growth rate of sauropods during this stage was influenced by high food intake and efficient digestion. Young individuals experienced rapid skeletal expansion, with bones elongating and strengthening over time. The neck continued to extend through vertebral growth, allowing increased feeding reach into plant canopies and ground vegetation zones. The tail also developed additional vertebrae, contributing to balance and movement coordination. Environmental conditions during this period supported large herbivore populations. Plant life included conifers, cycads, and ferns that formed extensive vegetation coverage in many regions. Sauropods moved through these areas in search of food resources, with their feeding patterns shaping plant distribution in some locations. Their movement involved slow, steady locomotion, supported by strong limb bones and stable joint structures. By the late Jurassic period, around 140 million years ago, some sauropod lineages developed extreme body lengths, supported by further skeletal refinement. Their vertebrae showed advanced internal structures that reduced weight while maintaining strength for support of neck and tail systems. Ligaments along the spine provided additional stability, allowing controlled movement during feeding and locomotion. The skull structure of these sauropods remained relatively small in proportion to body size. This reduced energy requirements for head movement while allowing efficient feeding access. The teeth were replaced continuously throughout life, ensuring consistent ability to process plant material. Jaw movement was generally simple, focused on stripping and gathering vegetation rather than complex chewing actions. As sauropods continued to evolve into the early Cretaceous period, around 130 million years ago, environmental changes influenced plant diversity and distribution. Flowering plants began to appear during this time, gradually altering available food sources. Sauropods adapted by maintaining flexible feeding patterns that allowed them to consume a wide range of plant types, including conifers and early flowering plant forms. The internal structure of sauropods continued to show adaptation for weight management. Bone cavities became more widespread and muscle attachment points adjusted to support long neck movement. The nervous system extended along the spinal column, with enlarged regions controlling limb coordination and balance. Sensory systems allowed detection of environmental changes such as movement, sound, and vegetation presence. Growth patterns in sauropods involved continuous development throughout life stages. Juveniles increased in size rapidly during early years, and adults continued to grow at slower rates over long periods. This growth pattern allowed gradual adaptation of skeletal structure to support increasing mass and feeding requirements. The digestive system expanded in capacity, allowing large amounts of plant material to be processed continuously. By the mid-Cretaceous period, around 100 million years ago, sauropod diversity remained present in many land environments. Their body forms showed variations in neck length, tail structure, and limb proportions. Some lineages developed wider body frames supported by robust limb bones, while others maintained more elongated body shapes with extended neck systems. These variations allowed occupation of different feeding zones within plant environments. Reproductive behavior continued to involve egg-laying in ground nests. Hatchlings emerged at small size and entered rapid growth phases, supported by plant intake. Juvenile survival depended on access to vegetation and suitable environmental conditions for feeding. Growth into adult forms involved continuous skeletal expansion and muscle development, with long neck structures becoming fully functional during later stages of development. During later evolutionary stages in the Cretaceous period, around 90 million years ago, sauropods maintained their presence in several regions of the world. Their skeletal systems reached high levels of specialization for supporting long body structures. Vertebrae were highly modified with complex internal chambers and reinforcing structures that distributed mechanical load across the spine. The tail remained important for balance and movement control, with muscular systems allowing adjustments during locomotion and feeding posture changes. Feeding behavior involved continuous browsing of plant material from different vertical levels in vegetation. The neck allowed access to food sources across wide spatial ranges without requiring extensive movement of the entire body. This supported energy efficiency in feeding patterns. Digestive processes remained slow and continuous, allowing breakdown of plant fibers through internal fermentation systems. Environmental changes during this time included shifts in plant distribution and climate patterns in some regions. Sauropods adjusted by moving across broad land areas in search of suitable vegetation zones. Their movement patterns were influenced by availability of food resources and water sources necessary for plant growth. Their skeletal and muscular systems supported long-distance movement over land surfaces with stable ground structures. The nervous system of sauropods continued to develop coordination across large body lengths. Signal transmission along the spinal cord allowed controlled movement of neck, limbs, and tail. Sensory input from the environment supported navigation through vegetation and terrain variations. Their eyes and nasal structures provided information about surroundings relevant to feeding and movement. Bone growth in sauropods remained influenced by metabolic processes that supported continuous tissue development. Mineral deposition in bones contributed to strengthening of skeletal structures over time. Air-filled cavities within bones reduced density while maintaining structural support for mechanical stress during movement and feeding. In later stages of sauropod evolution, body size and structural specialization reached stable patterns that allowed long-term survival in various ecological zones. Their presence influenced plant distribution through feeding activity, and their movement patterns affected ground vegetation structure. Juvenile and adult stages maintain different feeding requirements, with younger individuals focusing on accessible vegetation, while adults reached higher or broader feeding areas through neck extension. The evolution of giant sauropods involved continuous biological changes across millions of years, with gradual modifications in skeletal structure, digestive function, respiratory systems, and movement coordination. These changes occurred across long time periods and were influenced by environmental conditions, plant availability, and biological development processes that shaped their anatomy and behavior in land ecosystems across different geological stages, continuing through successive generations with ongoing adaptation in form and function. Earth during the time of the Jurassic period was a world where living things increased in number, size variation, and spread across many regions of land, water, and air. This time came after the end of the Triassic time and before the beginning of the Cretaceous time. It covered a very long span of Earth's history, during which many forms of life continued to develop in response to changing conditions on the planet. Dinosaurs became one of the most widespread groups of animals on land, and their presence was seen in many different environments across the globe. Other living organisms also developed at the same time, forming complex living systems in different habitats. Land environments during this time supported large areas of plant growth. These plant systems included many types of vegetation that spread across wide regions. Plants grew in warm conditions in many places, and this supported continuous feeding activity for plant-eating dinosaurs. Leaves, stems, and other plant materials were available in large amounts in many areas. This allowed plant-eating dinosaurs to move across different regions while feeding regularly. Their movement patterns were closely connected to the distribution of plant growth, and they spent much time in areas where vegetation was abundant. Plant life also supported smaller animals and insects that lived within the vegetation zones. Different types of dinosaurs lived on land during this time, and they had a wide range of body forms and sizes. Some dinosaurs had long neck structures that allowed them to reach plant materials located at different heights. Some had shorter neck structures and fed on plants close to the ground. Some dinosaurs had strong hind limbs that supported movement across open land areas, while others had body forms suited for slower movement within dense vegetation. Each type of dinosaur had body features that matched its way of feeding and movement. These differences allowed many types of dinosaurs to live in the same general regions while using different resources. Carnivorous dinosaurs were also present during this time and lived by feeding on other animals. These animals moved through land areas in search of food and used physical strength and movement abilities to capture prey. Their teeth structures were suited for cutting and breaking flesh, and their jaws were built for consuming meat. They shared environments with plant-eating dinosaurs, and both groups lived within the same ecosystems. The interaction between different feeding groups formed part of the natural life cycle on land during this period. Movement patterns of predators were influenced by the availability of prey animals in different regions. Land environments during this time were not the same everywhere. Some regions had thick vegetation that created dense living areas for many animals. Some regions had open land surfaces where movement was easier and visibility was greater. Other regions had areas with frequent water presence, such as rivers, lakes, and wetlands. These different environments supported different forms of life and allowed animals to live in places that suited their body structures and feeding needs. Animals moved within and between these environments depending on food availability and environmental conditions. water environments also supported a wide range of life forms during this time. Oceans contained many marine reptiles and fish species. Rivers and lakes supported freshwater organisms that lived in stable water conditions. Marine reptiles had body structures adapted for swimming and movement in water. They fed on fish and other aquatic organisms found in their environments. These water systems formed an important part of Earth's living structure during this time and supported continuous life activity in aquatic regions. Air environments were also occupied by living creatures during this period. Flying reptiles existed and moved through the air while searching for food or traveling between locations. These animals had wing structures that allowed them to move through airspaces. They fed on small animals or other available food sources depending on their environment. Their presence in the air added another level of living activity above land and water environments, creating a complete system of life across multiple layers of the planet. Plant life during this time continued to expand and change in distribution across the planet. Forest-like environments existed in many regions, supporting continuous plant growth. These plant systems provided energy sources for many herbivorous dinosaurs and other plant-eating organisms. The relationship between plant growth and animal feeding supported stable living conditions for many species. Plants also contributed to soil development and environmental stability in different regions. The Cretaceous period began about 145 million years ago and continued until about 66 million years ago. During this long span of time, life on land, in water and in the air developed into many different forms. Dinosaurs were present in very large numbers and existed in many types of body forms, sizes and feeding habits. This time was part of the Mesozoic era, and it held a very long stretch of Earth history, where living things spread into many environments and filled many ecological roles. The land surfaces were shaped by moving tectonic plates, and new oceans formed while older connections between land areas changed over time. These changes affected the living world in many ways and allowed different groups of dinosaurs and other organisms to develop in separate regions. At the beginning of this period, the arrangement of land was not the same everywhere. Large land areas were still present, but they were breaking into smaller sections. This breaking of land created separation between animal groups. When populations became separated, they followed different paths of development. Over many millions of years, this separation led to many new types of dinosaurs appearing. These dinosaurs developed in different environments, such as forests, river systems, deserts, coastal regions, and inland plains. Each environment provided food sources and living conditions that supported different body structures and feeding patterns. Plant life during this time also changed significantly. Flowering plants began to appear during the early part of the Cretaceous period. Before this time, most plant life on land consisted of conifers, cycads, ferns, and other non-flowering plants. As flowering plants spread across many regions, they became part of the food system for many animals. Leaves, stems, seeds, and fruits provided new types of plant material for herbivorous dinosaurs. These plant types developed in many forms, including small ground plants and taller woody forms. The presence of flowering plants influenced feeding habits and movement patterns of many dinosaurs, as plant distribution became more varied in different environments. Herbivorous dinosaurs during the Cretaceous period developed many different feeding structures. Some had teeth shaped for cutting plant material, while others had teeth suited for grinding tough vegetation. Jaw structures also varied, allowing different feeding methods. Some dinosaurs had broad mouths for collecting large amounts of plant material, while others had narrow beak-like structures for selective feeding. Body sizes varied widely, and some herbivorous dinosaurs grew to very large sizes, while others remained smaller and more agile. Herd behavior is observed in fossil evidence for some species, where groups of individuals move together in search of food and water sources. These behaviors helped these animals access feeding grounds across large land areas. Carnivorous dinosaurs also developed in many forms during this time. They occupied roles that involved feeding on other animals, including herbivorous dinosaurs and smaller creatures. Their teeth were shaped for tearing flesh, and their jaws were structured to deliver strong biting forces. Some carnivorous dinosaurs had long legs adapted for movement across open land areas, while others had shorter limbs and stronger bodies suited for ambush-style feeding habits. Fossil evidence shows that some carnivorous species grew to very large sizes, while others remained small and fast-moving. These differences in body structure allowed them to use different feeding strategies depending on available food sources and environmental conditions. In marine environments, the Cretaceous period supported many forms of life. Large reptiles lived in ocean waters, along with fish, ammonites, and many types of invertebrates. These marine reptiles had flippers or paddle-like limbs that helped them move through water. Some had long bodies and long tails that assisted in movement, while others had shorter bodies and more compact structures. The ocean environment provided a wide range of feeding opportunities, and marine reptiles developed feeding habits that matched available prey, such as fish and smaller marine animals. Coral systems and other underwater structures provided shelter and feeding grounds for many marine species. The air environment during the Cretaceous period included flying reptiles and early birds. Flying reptiles had wing structures, supported by elongated finger bones, and they were able to move through air spaces in search of food. Early birds developed feather structures that supported flight and other forms of movement. These birds had beaks and claws that allowed them to feed on insects, small animals, and plant materials. Forested regions provided shelter and nesting areas, while open areas allowed movement across larger distances. Air movement patterns and climate conditions influenced how these flying animals moved and fed across different regions. Climate conditions during the Cretaceous period were generally warmer than many later periods of Earth history. Polar regions did not have large ice sheets, and many areas experienced conditions that supported plant growth and animal activity throughout the year. Rainfall patterns varied across regions, with some areas receiving frequent rainfall and others experiencing more dry conditions. These climate conditions influenced plant distribution and animal movement. Rivers and inland waterways provided sources of water and supported ecosystems along their banks. Seasonal changes affected food availability and movement patterns of many dinosaur species. Fossil evidence from the Cretaceous period shows that dinosaur diversity reached very high levels. Many different groups existed at the same time, each adapted to specific environments and feeding habits. Some dinosaurs had armored bodies with protective structures covering their skin. These structures helped protect them from physical harm. Other dinosaurs had horned faces or head structures that may have been used for display, feeding, or interaction with other members of their species. Some had long necks that allowed them to reach vegetation at different heights. These physical features developed over long periods of time through gradual changes across generations. Reproduction among dinosaurs during this time involved egg-laying. Fossilized nests have been found in several locations, showing that some species return to specific areas to lay eggs. These nesting areas sometimes contained large numbers of eggs arranged in groups. Hatchlings that emerged from these eggs grew and developed in environments where food and shelter were available. Parental behavior in some species involved guarding nests or remaining nearby for protection during early stages of development. Growth rates varied among species, with some reaching adult size in shorter periods of time and others taking longer periods to fully develop. The distribution of dinosaurs across land areas was influenced by the separation of continents. As land masses moved apart, populations of dinosaurs became separated and developed in different directions. Over many millions of years, this separation led to the appearance of many unique forms in different regions. Fossil discoveries in various parts of the world show that similar types of dinosaurs appeared in separate regions, but with variations in body structure and size. These variations developed due to differences in environment, food availability, and long-term separation of populations. In forested environments, many dinosaurs moved among trees and vegetation. Some species developed long limbs that allowed movement through dense plant areas. Others developed body structures that allowed them to remain close to the ground while feeding on low-growing plants. Forest floors contained fallen plant material, insects, and small animals that formed part of the food system. Trees provided shade and shelter and also supported ecosystems that included birds, insects, and small reptiles. These forest systems were widespread in many regions during the Cretaceous period. In open land environments, dinosaur species moved across wide areas in search of food and water. These areas supported large plant-eating dinosaurs that consumed large amounts of vegetation. Fossil evidence shows that some of these dinosaurs moved in groups, which allowed them to cover large distances while searching for feeding areas. Carnivorous dinosaurs also used these open environments to search for prey. Movement patterns of these animals were influenced by seasonal changes, water availability, and plant growth cycles. Rivers and coastal environments supported additional forms of life. River systems carried nutrients across land areas and supported plant growth along their banks. These areas provided food and water for many dinosaur species. Coastal environments contain mixtures of land and marine life, where animals could access both land-based and water-based food sources. These environments supported a wide range of organisms and contributed to the diversity of life during the Cretaceous period. Small animals such as insects, early mammals, and reptiles also existed during this time. These animals lived in many environments and formed part of the food system. Early mammals were generally small and lived in hidden or protected areas, such as burrows, forest floors, or rocky regions. Insects existed in very large numbers and occupied many ecological roles, including feeding on plants, decaying material, and other organisms. Reptiles of smaller size lived in both land and water environments and contributed to ecological balance through feeding interactions. Changes in Earth's surface during the Cretaceous period affected volcanic activity and the formation of new land structures. Volcanic regions released gases and minerals into the environment, which influenced soil composition and plant growth. New land formations created additional habitats for living organisms. These changes occurred over long periods of time and affected the distribution of plants and animals across different regions. The asteroid impact hypothesis explains a major event in Earth history where a large space rock struck the planet and caused wide changes in living conditions across land, sea, and air. This idea focuses on how the arrival of an object from space set off a series of physical and environmental processes that affected living organisms and natural systems on a global scale. The event is commonly linked with a time near the end of the Cretaceous period, when many forms of life on Earth were already widespread in oceans, forests, and other environments. The object involved in this hypothesis is described as an asteroid that came from space and moved toward Earth under the influence of gravitational forces. As it approached the planet, it gained speed due to the pull of Earth's gravity. When it reached the atmosphere, it entered at extremely high velocity and began interacting with atmospheric gases. This interaction caused heating and compression of air in front of it, which led to intense energy release before and during the moment of impact with the surface. The place where the impact is believed to have occurred is in a region that is now part of the Yucatan area. At the time of impact, the ground in that region contained layers of rock such as limestone, along with deposits rich in sulfur compounds. When the asteroid struck, the energy released at the point of contact caused immediate breaking, melting, and vaporization of both the asteroid material and parts of the Earth's crust. Large amounts of rock and dust were thrown into the air and reached very high altitudes in the atmosphere. The impact produced a deep circular structure in the ground that later became buried under layers of sediment over long periods. The force of the impact also generated strong movement of water in nearby ocean areas. This movement spread outward in different directions and affected coastlines far from the impact location. Water displacement occurred due to sudden changes in the shape of the sea floor and the transfer of energy into ocean water. In the atmosphere, the impact introduced vast amounts of fine particles, dust, and vaporized material. These particles spread across different layers of the atmosphere and remained suspended for extended periods. The presence of this material affected the passage of sunlight toward the surface of Earth. Sunlight was reduced in many regions due to blockage and scattering caused by airborne particles. This change influenced temperature conditions at the surface and altered normal environmental cycles. The impact also released gases from both the asteroid and the ground materials. Sulfur-rich rocks contributed sulfur compounds into the atmosphere, while carbon-rich rocks released carbon-based gases. These gases mixed with atmospheric moisture and formed compounds that fell back to the surface in precipitation. This process resulted in acidic precipitation in various regions. The acidity affected water bodies, soil layers, and living organisms that depended on stable environmental conditions. After the impact, fires were initiated in many areas due to heat generated by falling material and thermal radiation. Vegetation on land experienced ignition in different regions depending on exposure to heat and hot debris. The burning of plant material added additional smoke and carbon particles into the atmosphere. These particles further increased the amount of material blocking sunlight and changed atmospheric clarity. The reduction of sunlight reaching Earth's surface affected photosynthesis in plants. Photosynthesis is a process where plants use sunlight to produce energy for growth. With reduced sunlight, many plants experienced interruption in their growth processes. This affected plant survival in various environments, including forests, plains, and coastal regions. Plants that could not adapt to reduced light availability experienced decline in function and survival. Marine environments were also affected by changes in sunlight and temperature. Microscopic organisms in ocean water depend on sunlight for energy production or for supporting food-based interactions. With reduced sunlight, these organisms experience changes in their activity levels. This influenced the availability of energy sources for other marine organisms that depend on them. Changes in water temperature also affected chemical balance in ocean environments. The atmospheric particles gradually began to settle back to Earth over time. As this settling occurred, some regions experienced deposition of fine dust layers. These layers covered soil and water surfaces and influenced the interaction between living organisms and their environment. The settling process occurred over extended periods rather than immediately after the impact, allowing atmospheric effects to continue for a long duration. The asteroid impact hypothesis also includes the effect of shock waves produced at the moment of impact. Shock waves are intense movements of energy through solid, liquid, and gaseous materials. These waves traveled through the ground and atmosphere, causing disturbances far from the point of impact. Ground movement affected rock layers and soil structures, while atmospheric movement influenced weather patterns in different regions. Ocean systems were affected by the displacement of water masses. When the asteroid struck the ocean floor or a nearby area, energy transferred into water created large-scale movement. This movement affected coastal zones and underwater environments. Sediments were disturbed and marine habitats experienced changes in structure. The redistribution of water also influenced temperature distribution in ocean layers. The hypothesis also explains that soot and carbon particles in the atmosphere played a role in blocking sunlight. Soot is produced when organic material burns without complete combustion. Large fires in vegetation-rich areas contributed to soot formation. These particles remained suspended in the atmosphere and reduced the clarity of incoming solar radiation. The reduction of sunlight affected temperature conditions on land and in shallow water environments. Temperature changes occurred due to reduced solar energy reaching the surface. With less energy from sunlight, surface conditions experienced cooling trends in many regions. This change influenced the behavior of living organisms that depended on stable temperature conditions. Some organisms adapted by changing behavior or moving to different environments, while others were unable to adjust to altered conditions. The chemical changes in the atmosphere also affected water systems. When sulfur compounds combined with water vapor, acidic substances formed and returned to the surface through precipitation. This affected freshwater bodies such as rivers and lakes, as well as soil composition. Living organisms in these environments were exposed to altered chemical conditions that influenced their survival and reproduction processes. In marine environments, changes in water chemistry affected organisms that build shells or skeletons from dissolved minerals. Altered chemical conditions influenced the availability of these minerals in seawater. Organisms that rely on stable mineral conditions experience disruptions in their biological processes. This affected populations in various ocean regions. The asteroid impact hypothesis includes the idea that dust and aerosols remained in the atmosphere for extended durations due to their fine size and distribution across multiple atmospheric layers. These particles interacted with sunlight and scattered it in different directions. This scattering reduced the amount of direct sunlight reaching the surface and influenced environmental processes dependent on solar energy. The movement of atmospheric particles also influenced wind patterns. As temperature distribution in the atmosphere changed, air movement patterns adjusted in response. This led to changes in weather systems in different regions. Rainfall distribution was affected, and some areas experienced changes in precipitation timing and amount. These changes influenced soil moisture levels and water availability for living organisms. Vegetation on land responded to the reduction in sunlight and changes in precipitation. Many plant species rely on consistent environmental conditions for growth cycles, seed production, and reproduction. With changes in light and moisture availability, these cycles were disrupted. This affected plant populations in different geographic areas and altered the structure of plant communities. Herbivorous organisms that depended on plant material for food experienced changes in food availability. With plant growth affected, feeding patterns and survival conditions for these organisms were influenced. This also affected organisms that depended on herbivores as part of their own food intake processes. The changes spread through different levels of ecological systems involving living organisms and their interactions. The asteroid impact hypothesis also considers the effect of long-term atmospheric dust removal. Over time, gravity caused particles to fall back to Earth, gradually reducing atmospheric density of suspended material. As this process continued, sunlight began to reach the surface in increasing amounts. However, the environment had already undergone significant changes due to earlier conditions, and recovery processes depended on multiple environmental factors. In aquatic systems, the reduction of sunlight affected organisms at different depths. Surface waters experienced more direct influence from atmospheric changes, while deeper water layers were affected through changes in temperature and nutrient distribution. The movement of nutrients in water systems was influenced by changes in runoff from land and altered precipitation patterns. Chemical deposits from atmospheric particles entered soil systems and water bodies. These deposits altered nutrient availability in different environments. Some organisms responded to these changes by adjusting physiological processes, while others experienced disruption in growth and reproduction. Soil composition changes also affected plant root systems and their ability to absorb nutrients. The asteroid impact also generated heat energy that caused melting and transformation of rocks near the impact site. This process created materials that were ejected into the atmosphere as molten droplets. As these droplets cooled, they formed small solid particles that later fell back to Earth. These particles became part of sediment layers in different regions. The distribution of ejected material depended on atmospheric movement and gravitational settling. Fine particles traveled through air currents before settling in distant locations, while heavier particles fell closer to the impact area. This distribution pattern influenced geological layers formed after the event and provided physical records of the impact process. The hypothesis includes the role of energy transfer through different Earth systems. Energy from the impact was transferred into ground motion, atmospheric heating, ocean movement, and chemical reactions. Each system responded according to its physical properties and conditions at the time. These interactions influenced environmental stability in multiple regions of the planet. The mass extinction event at the end of the Cretaceous period was a major turning point in the history of life on Earth. It took place about 66 million years ago, and it affected a very large portion of living organisms across land, oceans, and the air. Many groups of animals and plants disappeared during this time, including a wide range of dinosaurs that had lived for many millions of years. The event marked a sudden change in the composition of life forms on Earth, and it reshaped the direction of biological development in the periods that followed. During the late part of the Cretaceous period, Earth had many different environments that supported a wide range of life. Land areas contained forests, open regions, river systems, and coastal zones. Oceans contained many types of marine reptiles, fish, shell organisms, and microorganisms. The air was filled with flying reptiles and many types of insects. Dinosaurs occupied many land environments, with herbivorous types feeding on plants and carnivorous types feeding on other animals. Many plant groups, such as flowering plants, had already become widespread and formed important parts of ecosystems. In the final stages of the Cretaceous period, signs of environmental change began to appear in different parts of the planet. These changes involved shifts in climate patterns, changes in sea levels, and variations in the distribution of plant life. Some regions experienced changes in rainfall patterns and temperature conditions that affected plant growth. These changes influenced the availability of food sources for many herbivorous animals, which in turn affected carnivorous animals that depended on them. At the same time, Earth was experiencing geological activity. The movement of large sections of the planet's surface was ongoing. Volcanic activity was present in several regions, releasing gases and molten rock into the environment. One region with significant volcanic activity was an area that is now part of modern-day India. This activity produced large quantities of volcanic material over extended periods of time. The release of gases, such as carbon dioxide and sulfur compounds into the atmosphere, contributed to changes in atmospheric conditions and air quality. Around the same time, a major extraterrestrial event occurred. A large object from space, often described as an asteroid, moved toward Earth and made contact with the planet's surface. This object struck an area that is now located near the Yucatan region. The impact released an extremely large amount of energy at the point of contact. The energy from this impact caused immediate physical changes to the surrounding area, including intense heat, shock waves, and the movement of large amounts of material from the surface. The material that was displaced during the impact entered the atmosphere and spread across wide regions of the planet. Dust, rock fragments, and vaporized material filled the air and reduced the amount of sunlight that reached the surface. This reduction in sunlight affected photosynthetic organisms, including plants and algae. When photosynthesis was reduced, the production of food energy in ecosystems was affected. Many organisms that depended on plant material experienced changes in food availability. The atmosphere also experienced changes in composition due to the material released during the impact and due to gases released from volcanic activity. Fine particles remained suspended in the air for extended periods. These particles contributed to changes in atmospheric clarity and altered the way sunlight interacted with the atmosphere. The reduction in sunlight reaching the ground affected temperature conditions and influenced environmental stability across many regions. In oceans, the changes in sunlight and temperature affected microscopic organisms that formed the base of marine food chains. These organisms include planktonic forms that depend on sunlight for energy production. When their activity was reduced, organisms that depended on them also experienced changes in food availability. Marine environments contained many types of organisms, including ammonites, marine reptiles, fish species, and coral systems. Many of these groups experienced severe reductions in population levels. On land, vegetation experienced widespread stress due to reduced sunlight and changes in atmospheric conditions. Plants that depended on regular sunlight cycles experienced reduced growth activity. As plant availability changed, herbivorous animals faced changes in food sources. This affected many types of dinosaurs and other plant-eating animals. Carnivorous animals that depended on herbivores also experienced changes in food supply conditions. The sudden nature of the impact event caused rapid environmental disruption in many regions. Fires occurred in areas where heat from the impact ignited vegetation. These fires contributed additional particles into the atmosphere. The combination of impact debris, volcanic emissions, and fire-related particles created a thick atmospheric layer that persisted for a period of time. Temperature conditions across Earth changed due to reduced solar energy reaching the surface. With less sunlight available for heating, many regions experienced changes in thermal balance. These changes influenced water cycles, plant activity, and animal behavior. Rivers, lakes, and coastal environments also experienced changes due to shifts in rainfall and evaporation patterns. Many species that were adapted to stable environmental conditions experienced difficulty adjusting to the rapid changes. Organisms with specialized food sources or habitat requirements were affected strongly because their survival depended on specific environmental conditions. General environmental stress affected reproduction, growth, and survival rates across many ecosystems. In terrestrial environments, dinosaurs represented a major group of animals present at the time. Different dinosaur groups occupied various ecological roles. Herbivorous dinosaurs fed on plant material, while carnivorous dinosaurs fed on other animals. Smaller animals, such as early mammals, reptiles, and insects, also lived in these environments. The disruption of plant life and changes in food availability affected all these groups in different ways. In marine environments, organisms such as ammonites, mosasaurs, plesiosaurs, and various fish species experienced changes in survival conditions. The reduction in plankton populations affected organisms that depended on them directly or indirectly. Coral systems that depended on stable environmental conditions also experienced stress due to changes in water temperature and chemistry. The extinction event did not occur in a single instant across all locations. Instead, it involved a sequence of environmental disruptions that took place over a period of time. The initial impact event caused immediate physical destruction in the surrounding region. Following this, atmospheric changes developed and spread globally. These atmospheric changes influenced sunlight availability, temperature patterns, and ecological systems over extended periods. Volcanic activity that was already occurring in different parts of the planet continued during this time. This activity released gases and particles into the atmosphere that contributed to environmental changes. The combination of volcanic emissions and impact-related atmospheric changes created conditions that affected ecosystems on a global scale. As time progressed, ecosystems began to show signs of collapse in different regions. Plant communities experienced reduced growth and changes in distribution. Herbivorous animals faced changes in feeding conditions. Carnivorous animals experienced changes in prey availability. Marine ecosystems experienced reductions in primary productivity and changes in food chain structures. Microorganisms that formed the base of many food chains played an important role in these changes. When their activity declined due to reduced sunlight and altered environmental conditions, the effects spread through multiple levels of ecosystems. Organisms at higher levels of food chains experienced changes in energy availability. Many species experienced significant reductions in population size. Some groups disappeared completely, others survived in limited numbers in specific regions where conditions remained suitable for survival. These surviving groups later became the foundation for future biological development in the following geological period. Soil conditions also changed due to the reduction in plant cover and increased deposition of dust and debris. Soil erosion increased in many areas due to the lack of stable vegetation. River systems carried increased sediment loads, which affected freshwater habitats. Aquatic organisms in freshwater environments experienced changes in water quality and habitat structure. The chemical composition of oceans also experienced changes. The input of particles and gases affected water chemistry, including acidity levels. These changes influenced marine organisms that depended on stable chemical conditions for survival. Shell-forming organisms were affected by changes in the availability of chemical components needed for their structures. The extinction event affected a wide range of life forms across different environments. It included organisms that lived on land, in water, and in the air. It involved both large and small organisms, including those that played important roles in ecosystems. The effects were not limited to a single group of animals or plants, but spread across many branches of life.